Welcome to S Chemistry. I'm your instructor Dr. Suhas Gaudi and I will be teaching BSc 5th semester Physical Chemistry course on spectroscopy. Here is the outline. First, I will introduce basic feature of different spectrometers, then followed by essential component of spectrophotometer, then statement of the Born-Oppenheimer approximation. Let's see what is meant by basic feature of different spectrometers. So as a definition, the spectrometer is the instrument which are used to study the absorption or emission of electromagnetic radiation as a function of wavelength are called spectrometers. So here we study both absorption as well as emission of electromagnetic radiation. So here the spectrometers used in various regions of the spectrum naturally differ widely from each other in construction. So there are two different types of construction are there. So major broad region is absorption spectrometer, another is emission spectrometers. So in this chapter we are going to learn about absorption instrument. So what is absorption instrument? So here an absorption spectrometer which might be used in infrared, visible and ultraviolet regions. So where electromagnetic radiation hits to the molecule and that energy get absorbed by the molecules, uh, we call it absorption instrument. So these regions, generally these kind of absorption take place in the regions of infrared, visible and ultraviolet regions. So now we will see essential components of spectrophotometer. So there are four essential compounds are there from chemistry point of view. So one is source, another is monochromator, third one is a sample holder, fourth one is detector, and amplifier and recorder are electronic parts. Now only these four parts we are going to see in this chapter. So first is a source. So what are the source? It should be cheap radiant energy source should be there. So then wavelength selector, monochromator also we consider as a wavelength selector. Third is a sample holder. Fourth one is a detector. Now first we will see radiant energy source. So for UV radiation, most commonly used radiation source is hydrogen lamp or deuterium lamp. These are bulbs consist of pair of electrode and provide with a quartz window. The bulb is filled with hydrogen or deuterium gas at low pressure. So hydrogen lamp or deuterium lamp are the same. Only deuterium is isotopes of the hydrogen. So this is commonly used for the UV radiation. So in that bulb, as you can see in this picture, so it's a pair of electrode. So two pairs are there, electrodes, and here the whole glass is made up of quartz because your radiation should not get absorbed by the any glass material. So that is the purpose of quartz window. So the bulb is filled with hydrogen and deuterium gas at low pressure. So inside water the bulb pressure is very low as compared to other bulbs. So when a stabilized high voltage is applied, they emit radiation which is continuous in the regions of 180 nanometer to 350 nanometer. So this range is corresponds to only UV radiation, and only this under this region it's a continuous source of electromagnetic wave. So sometimes people also used a xenon lamp for the UV source. So next source is for visible radiation. So for visible radiation we generally use the tungsten filament as shown over here. So it is the most commonly used and it's very inexpensive to get the visible radiation source. So it always emits radiation, continuous radiation in the regions between 350 nanometer to 3500 nanometer. It's a well-known source for the visible radiation. Third region is the infrared. For infrared, so nurse glower and glower are the most commonly used radiation source. So glower consists of silicon carbide rod, and it don't require any outer side any gas, because the silicon carbide is a very tough material, and with that this system with high temperature also it gets survived. And IR radiation is nothing but is heat radiation only, so that's why it don't require inert gas inside the bulb. So nurse glower of halo rod of zirconium and yttrium. So inside rod is a zirconium or yttrium. So these two metals are generally used for the infrared radiation source. Now we will see the wavelength selectors. So there are two types of wavelength selectors are there. One is a filter. So filter are a little bit old technique. So these are the material which absorbs all other light except one which they transmit. So filter generally is like two way. One side is absorbance, another side is transmission. So filter generally use uh, earlier used to instrument used to do use the gelation filter. They are made up of layer of gelatin and colored with organic dyes and sealed between glass plates. So these dyes are scaled between two glass plates. So that's how the filters are working. So only what are the suppose we have 550 nanometer filter is there, that is will coated with a gelatin filter. So only the 550 nanometer will get transmitted, remaining all other wavelengths will get absorbed or it will get reflected. So that's how the filter is work as a wavelength selector. So modern instrument use a tinted glass filter. So the filter resolve light into a relatively wide bandwidth is about 40 nanometer. So it's not exact 550 nanometer it will transmit. So it will like suppose if it's for 550, then this side below 550 20 and above 550 20 nanometer, the that range, that kind of range will be like bandwidth will be there for the filters. So that's why these are the commonly used only in the calorimeters. So calorimeter BSc students should be knowing because this is in practical. So only selected wavelengths we are going to scan in the calorimeter. So another type of wavelength selector is monochromator. So now the recent what are the instruments are there or spectrophotometers are there. So they generally use the monochromator. So monochromator is means only one chrome means color, mono means one. So only one color they are going to use at a time. So that is the purpose of monochromator. So these are used to select a particular wavelength from a polychromatic light. Polychromatic light, so these are used to resolve polychromatic light into monochromatic light. So your source is polychromatic always. So it has various wavelength. So only one kind of light it's going to be resolved. So that's how it work. So the essential component of monochromators are first one will be the entrance slit, lens or mirror. Second part is the collimated devices, collimating devices, such as we will see in upcoming slides. And third essential component of monochromator is wavelength resolving device like prism or grating. So in collimating devices, we generally use the lenses or mirrors. So here D is the focusing, the fourth one is the focusing lens or mirror, and fifth one is the exit slit. So these are the five essential components of the monochromators are there. So second one, now we are going to see wavelength selector as a monochromator. So first one is a prism. So prism disperse light into its constitute wavelength by virtue of its ability to reflect different wavelengths to a different extent. So that's how the prism we work. So everybody is well known about the prism. So it is a triangular shape. So here you can see in this figure. So prism is a three-dimensional object where the material it is made up of either glass or quartz. So depending on the material, we are going to resolve different type of wavelengths. So depending on which kind of prism we are using, so based on that you will get the uh, dispersion of light in the specific region. So for visible region, we use simple glass prism. So like that, only one source of light is there. So this light is getting separated due to path difference in the prism. So this path difference is there. That's why the wavelengths are getting separated. So that's how the prism work as a monochromator. So for UV region, we use quartz prism, and for IR regions, we use ionic crystalline prism. So these are the one kind of monochromators. So another type of monochromator is gridding. So gridding are nowadays griddings are widely used. So in UV visible and IR spectrophotometer, gratings are used. So a diffraction grating consists of a glass or ceramic plate into which fine grooves have been cut about 1,000 nanometer apart and covered with a reflective aluminum coating. So this is made up of either glass or ceramic plate, and there are like cuts will be there. So you can see like below figure. So this kind of cuts will be there. So each cuts will be around 1,000 nanometer apart. So this distance to this distance will be 1,000 nanometer, and the coating is completely reflective. So aluminum coating will be there. So whatever the rays coming inside, it will get reflected only. So there is no transmission over here in this grating. So the grating resolve into its component wavelength by virtue of constructive and destructive interference of radiation reflected. So whatever the reflection is there, there two possibilities are there. One is interference is constructive, and other will be destructive interference will occur uh, on the reflected rays. So that's how we are getting uh, different kinds of monochromatons wavelength. Now we will see the third essential component of spectrophotometer is sample holders. So now your sample has to be put in particular holder. So that's why the sample to be studied in the UV visible regions are usually gases or solutions, and are put in cell known as a cuvette. So the sample holder name is a cuvette. So there are different types of cuvettes are there. First, we'll see for the visible region. So simple glass cuvette will be used. So this is one of the example of cuvettes. So this is like in kind of a square. So inside you can put your solution, and you can put the lid on to the top of that. So your solvent should not get evaporated whatever the inside is there. So these cuvettes are generally simple glass cuvettes are generally used for the visible regions. For UV regions, for ultraviolet regions, the quartz fused silica cuvettes are generally used. So this it's look like same, but the little bit quartz cuvettes are little bit heavier than the simple glass, and it is a good material. So under UV regions, so that in that region there will be no absorbance of the quartz material. So that's why these quartz cuvettes are generally used for the UV regions. Third is the infrared regions. For these regions, we generally use the palettes. Uh, so that palette is made up of sodium chloride or potassium bromide. So these are the palettes. So example of KBR palette is here. So as shown in this figure. So it is a circular disc. You can put your sample, liquid sample over here. Otherwise, if your sample is solid, you can put in sodium chloride salt, and like 1:10 ratio. Your sample should be 1 and 10 will be your sodium chloride. That's how if you crush it, you have to make this kind of palette. So people are generally used as a, for this infrared region. Now we are going to see the fourth component, essential component of spectrophotometer is detector. So for UV visible radiation, there are various types of photodetectors are there. So first one is a photocells or phototubes, and photomultiplier tubes are used for UV visible radiation. Now we are going to see about the photocells. So photocells, these detectors are based on the selenium, and the photocells are used. Selenium based photocells are used. Second is photo tubes or photoemissive tubes. So here phototubes consist of evacuated glass envelope with a quartz window, semi-cylindrical cathode whose inner surface is coated with alkali or alkaline earth oxide. So and centrally located metal wire anode. So you can see in this picture. So this is general figure of photo tubes or photoemissive tubes. So basically the this completely is based on photoelectric effect, as you have seen in the first chapter. So here uh, this is the second type of photoelectric device, that is in vacuum. So which consists of semi-cylindrical cathode and wire is anode sealed inside evacuated transparent envelope, as you can see in this figure. So outer case is made up of a complete quartz. So here your photon beam will fall on this cathode, and it will get transmitted to the this photo will transmit to the wire anode. So the concave surface of electrode supports a layer of photoemissive material that tends to emit electron when it is irradiated. So when a voltage is applied across electrode, the emitted electron flow to the wire anode, generating a photocurrent. So that is generally about 1/10 as great as that associated with photovoltaic cell for a given radiant intensity. So in contrast, however, amplification is easily accomplished because the phototubes has a high electrical resistance. So the number of electron ejected from photoemissive surface is directly proportional to the radiant power of the beam that strike that surface. So as the voltage applied across the two electrode, the tube is increased, the fraction of emitted electrons that reaches the anode rapidly increases. So when saturation voltage is achieved, essentially all of the electrons are collected at the anode. So the current then become independent of voltage and directly proportional to the radiant power. So phototubes are usually operated at the voltage of about 90 volt, that is the DC volt. So over given in this figure. So it's a well within the saturated region. So here I have shown also how it look like in real uh, way. So this is a this much small. So RCA is the one of the company who make this kind of phototubes or photoemissive tube detector. Now we are going to see another part type of detector, that is photomultiplier tube. So photomultiplier consists of an evacuated glass tube into which are scaled the cathode and the anode and additional intervening electrode known as dynode. So here are three different compounds are there. One is cathode, another is anode, and third is dynode. So between cathode and anode, in between there will be diode. So for higher region, photoconductive cells are used. So these diodes, and for middle and far higher regions, rapid responsive thermometers such as thermocouples, bolometers and gas thermometers are used. So now we will see how photomultiplier tube works. So here is the basic figure I have shown over here. So for the measurement of low radiant power, photomultiplier tubes offer advantages over ordinary phototubes. So previously we have seen phototubes, but if your signal is very low, low power, low radiant power, then photomultiplier tube is useful detector. So well, in this figure schematic diagram we have shown for a device. So photocathode surface is similar in composition to the surface of phototubes described in figure. So as it emits electron when exposure to radiation, so the tube also contain additional electrodes called diodes. So here diodes are shown here. So there are various types of diodes. There is a number of like 1 to 9. So diode 1 is maintained at voltage approximately 19 volt, more positive than cathode. So cathode has negative charge and diodes has the positive. So the electrons are accelerated towards it as a result. So each photoelectron that strikes the diode causes emission of several additional electrons. These electrons in turn are accelerated towards diode 2, which is minus 90 volt, so more positive than diode 1. So again, several electrons are emitted for each electron that strike the surface. So by the time this process has been repeated 9 times, so that's why the what are the energy like 10 to the power 6 to 10 to the power 7 uh, electrons have been formed for each incident photon. So that much time it get multiplied your signal. So now we are going to see the third point, that is statement of Born-Oppenheimer approximation. So as the sentence suggests, it is a statement who Born and Oppenheimer, there is no two different name of scientists who given the statement, and the statement is about approximation. So the statement is given like here: the molecular spectra arises from three types of transition, viz. Rotational, vibrational and electronic transitions. So according to Born-Oppenheimer approximation, the total energy of the molecule is given by this equation. So that is E equal to E E, that is mean by the summation of, that is the summation of these energy of the summation of translational energy, rotational energy ER, vibrational energy EV and electronic energy, that is EE. So these are the four types of energies are there. If you sum it, you will get the total energy. Okay, so energy order of this energy is like this with decreasing order. So here the translational energy is however not quantized. So the last one, this translational energy is not quantized. Remaining three types of energy are quantized. So this E electronic energy will be always higher than the vibrational energy, and this vibrational energy always greater than the rotational energy. So that's how the sequence is always will be there correspond to particular molecules. So since the vibrational energy is negligibly small, we can write the Born-Oppenheimer approximation as over here, given here. So E equal to, so whatever the translational energy, this term is got eliminated. So that's why we have taken as a 0. So remaining whole equation is in this way. So E equal to EE plus EV plus ER. So that is electronic energy plus vibrational energy plus rotational energy. So if you sum all these three, you will get the total energy of the molecules. So this is the Born-Oppenheimer approximation. So here we come to the end of this lecture. So here are the references for images and for the content I have shown over here. So here I say thank you for kindly listening me. See you in next lecture. Till then, happy learning.